We know that particles with identical charges naturally push away from each other, but if we force them together against their will, what happens to the physical effort we spent pushing them? Think about a familiar mechanical baseline. When you forcefully compress a physical steel spring, you are doing physical work. That work doesn't disappear. It gets trapped inside the coils of the spring. The same logic applies to gravity. When a motor drags a roller coaster car up a steep hill, it is working against the gravitational pull of the Earth, storing up that effort for a massive release later. Physicists call both the spring force and gravity conservative forces. In these specific systems, energy is never truly lost to the environment. It is simply saved for later. The Coulomb force between two electrical charges operates the same way. Because it relies on an inverse square law based on distance, just like gravity, it belongs in that exact same conservative category. So, just as mechanical work is stored in a compressed spring, the effort used to push against an invisible electric field must also be stored. We call this hidden, calculable property electrostatic potential energy. To see exactly how this work transforms into stored energy, look at this animated 2D coordinate system. We have a large positive charge, labeled Q, fixed permanently at the origin. Farther out, at point R, sits a smaller positive test charge, Q. The arrows radiating outward show Q's repulsive electric field. Because both charges are positive, our tiny test charge experiences an intense outward Coulomb force. It naturally wants to fly away from the origin. If we want to move that test charge inward to a closer location, say point P, we have to intervene. We must apply a direct external force against that natural repulsion. But there is a strict physical condition to do this properly. Our external push must exactly equal the repulsive force of the field. This means the charge is brought inward at an infinitesimally slow, constant speed, with zero net force and zero acceleration. Because we moved the charge without accelerating it, every ounce of mechanical work done by our external force is absorbed by the test charge, banking it directly as potential energy once it reaches point P. The moment you let go and remove that external force, the system reacts. That trapped potential energy is instantly unleashed. As the charge flies away, it gains kinetic energy and loses its potential energy in exact equal measure. The total energy of the system remains perfectly conserved from start to finish. This proves that the exact amount of mechanical work we performed to push the charge inward is the direct physical measure of the electrostatic potential energy gained by the system. But this raises a geometric question. What if we didn't push the charge in a straight, orderly line? What if we took a massive detour to get from the start to the finish? Take a look at these three travel routes through the electric field. Here, charge Q moves from point R to point P in a straight line. Then it takes a zigzag pattern. Finally, it travels in a wildly looping spiral. When we calculate the actual mechanical work done against the electric field, the numbers settle. The tally yields the exact same number for all three routes. Physicists call this path independence. It is the defining trait of a conservative force. The electric field does not care about your specific route. It only cares about where you start and where you end. Because the physical path is irrelevant, we know that every specific point in an electric field holds a strict, measurable potential energy difference relative to any other point in that space. Our core equation only calculates the difference in energy, not absolute energy. Absolute potential energy is physically meaningless. If you add an arbitrary constant, alpha, to both points, they cancel out when finding the difference. The baseline changes, but the difference remains exactly the same. However, to solve real-world problems and calculate precise exam answers, we must establish a standardized, universal zero point for potential energy. The solution is moving our starting point deep into space, to infinity, where the outward Coulomb force is practically non-existent. Thus, the potential energy of a charge at a specific point is the work done bringing that charge from infinity to that point. By anchoring our physical measurements to the concept of infinity, we can now mathematically map the invisible energy landscape of the universe, establishing the framework needed to calculate electric potential and design capacitors.